All right, so last time we used BRST symmetry to restrict the possibilities of divergences in a quantum theory. But that leads us to the possibility that perhaps we can use BRST symmetry itself in order to quantize a theory. So what would that mean? So specifically, BRST symmetry is a residual gauge symmetry, a global residual gauge symmetry. So what one does is you have a local symmetry, a gauge theory, and imposes a constraint, gauge fixing. And then we're left with this BRST symmetry. But we have seen that there was something that we did. Well, we didn't actually do, but we showed how it could be done to gauge theories when we gauge fix, namely the Dirac formalism for constrained quantum systems. And basically, BRST quantization is an extension of that. Well, it builds upon the Dirac formalism for constrained quantum systems, and uses the power of the symmetry to do more. And then actually there's a further extension known as Batalitsky-Vilskovitsky or BV, or field anti-field formalism, but we'll not be treating it here. I'll say a few words at the end about it. But to begin with, then let's just review the Dirac formalism, since BRST symmetry, BRST quantization is supposed to build upon it. So in the Dirac formalism, we have a classical theory obeying some constraints called primary constraints, Phi-m, that depend on the phase space Q and P. So there's capital M of them, and we want to quantize in such a way as to preserve these constraints. But since this is a function of phase space, we have to think about the fact that there's derivation with respect to phase space, in particular Poisson brackets, which later are extended to commutations, commutators or anti-commutators. And those things act primarily on phase space. So what we have to do is first act with these things and then put the primary constraints to 0. If we do that, we have what is called weak equality, and we'll write it as this tilde curly equal to 0. If, however, it doesn't matter whether I take derivatives with respect to the phase space or not, then we say we have strong equality, and in this case we put equal to 0. So in the Hamiltonian formalism, we know that the time evolution of a function of phase space is given by the Poisson bracket of the Hamiltonian with the function with Hamiltonian. But in the presence of these constraints, we can moreover add the constraints to the Hamiltonian with some coefficients um, and obtain also the so-called total Hamiltonian. And still we have evolution of the function of phase space, just that now the evolution is weakly equal to the Poisson bracket of the function with the total Hamiltonian. Now, the constraints, the primary constraints have to obviously be preserved by the time evolution. That's what constraints mean, having constraints on phase space. So that means phi dot have to be equal to 0, which means that in the Hamiltonian formalism that the Poisson bracket of phi m with the Hamiltonian should be equal to 0. Now, in terms of the total Hamiltonian, we can say again that the Poisson bracket of phi m with the total Hamiltonian is weakly equal to 0, or expanding the total Hamiltonian in the two terms, we get that the original term, the Poisson bracket of phi m with Hamiltonian plus this coefficient un times the Poisson bracket of phi m with phi n is weakly equal to 0. Now this is an equation. This is a new constraint. So the original constraint was just phi m, but now this is phi m, which by our definition is equal to 0, or weakly equal to 0 more precisely. And then this is a new kind of constraint called the secondary constraint. And then we can, so once we clean up this constraint and obtain something that I'll call some new phi with some other index, then we can repeat the procedure. Take the time evolution of that constraint and expand it like this and obtain a new constraint. And eventually, when you do this, this series ends. And then we have found all the so-called secondary constraints. And those will be denoted by phi k, with k going from m plus 1. M, remember, is the maximal, the total number of primary constraints, to m plus k, capital K. And the total number of primary and secondary constraints, phi m and phi k, will be called phi j. And I'll say phi j curly equal to 0, weakly equal to 0, with j going from 1 to m plus k, capital. Then we define a first-class function as a function of phase space R of Q and P if its Poisson bracket with all the constraints, phi j, is weakly equal to 0. That is, R with phi j curly equal to 0. Curly equal to 0 means, in particular, that it's a linear combination of the phi j's. That is equal to sum over j prime, r j j prime, phi j prime. So a first-class function, so this is true for any first-class function. But now, if I consider the phi a, it's the R to be a phi a itself, or phi j itself, this would also be a first-class. This could also be a first-class constraint. And then, so if such phi a is a first-class function, that is a first-class constraint, in that case, I would say that phi a Poisson bracket with phi j is, something that has now an index a and also a and j, and another j prime that's signed over with phi j prime. And as you see, this is the form. So the bracket here is Poisson bracket, but other than that, besides, we know that finally in the Dirac quantization, the Poisson bracket goes over the commutator. So this looks then like an algebra, right? And then the F's look like the structure functions, or structure constants, or functions, depending, of the algebra. Now, I said that one phi a could satisfy this, but there are other phi a's that could not satisfy this for all the phi j's. So a first-class constraint would be some phi a for which phi a with all of the phi j's is weakly equal to 0. But if there is a phi j for which the phi are looking at is not weakly equal to 0, then we call that function phi a second-class constraint. Basically, second class is something that's not first class. So since phi j are the full set of the constraints, for primary and secondary, that are obtained from time evolution, and ht is time evolution up to weakly equality, that means phi j with ht is weakly equal to 0, and then expanding ht, I get this. But this equation then can be thought of and as a set of, this set of equations for all j's can be thought of as a set of equations for the coefficients um. And this has a particular solution that I'll call capital Um to this equation, which I'll call the inhomogeneous equation, thinking of, say, for instance, second-order differential equations, homogeneous versus inhomogeneous, plus linear solutions of the homogeneous equation with some arbitrary numerical coefficient VA. So the homogeneous equation means without this first term, that the Poisson bracket with the Hamiltonian. So only VAM with phi j times phi m is weakly equal to 0. So then I write the total Hamiltonian as the Hamiltonian plus this particular solution um with multiplying phi m, and then remember these are coefficients, right? So little um was written as big um, solution of the inhomogeneous equation, plus capital VAM, solution of the homogeneous equation, times phi m. And now I can redefine. I can call this. Here is capital V. Capital VAM phi m. I can call phi a, some particular type of constraint, and then H prime. I'll be calling H prime this first term here, H plus the particular solution times the constraints. So by definition, by this definition of the homogeneous equation, you see that these phi a's, which are VAM times phi m, since Poisson bracket with all the phi j's is weakly equal to 0. By definition, this phi a is first class. But also, since UM is a particular solution of the inhomogeneous equations, we have that if I take this H prime, so I have this plus the particular solution commuted with all the phi j's. This H prime is also first class, since Poisson bracket with all phi j is equal to 0. However, while first class versus second class has a very clear definition, very clear difference in meaning, primary versus secondary does not. Primary is what we start with, but doesn't matter what we start with. And all that matters is the complete set. So we can define then the extended Hamiltonian by adding also the first class but secondary constraint, which I'll be calling VA prime phi a prime. So HT was H prime plus VA phi a, and then HE is that plus VA prime phi a prime. Now, to quantize, we need to define brackets that replace the Poisson brackets. Usually, those brackets were commutators. But in the case of Dirac quantization, the bracket that the other way around. So in usual quantization, the Poisson bracket is replaced with commutator. But now we have to define brackets that replace the Poisson bracket. So brackets that, when quantizing, go over to commutators. And why do we need to do this? We need to do this because these second-class constraints that, the second-class constraints don't Poisson commute with other phi j's, so create create a potential problem because you don't know how to do with commutators when quantizing, how to deal with them. So since the second class constraints are the problem, and moreover we can find a set of independent second class constraints by eliminating all possible linear combinations, and then define CSS prime as the inverse matrix to this matrix of Poisson bracket of these chi's. So defined by this equation. And then the direct bracket is the Poisson bracket minus the Poisson bracket of f with chi s, then this CSS prime, which is chi s prime, chi s prime inverse, then chi s prime with g. By defining this, the Dirac, the time evolution using the Dirac brackets is the same as using Poisson brackets. Why is that? Well, I have so from the Dirac brackets itself. Sorry, from the HT. HT is H plus a combination of. Sorry, it's HT is H prime, which is first class, plus a combination of first class constraints. First class means that something with all the commutator with all the constraints, in particular with the second class constraints, is equal to 0. So replacing, so looking at the commutator of G with HT, so let's say G is HT, right? The point is that this second term must be equal to 0. So if I have here HT, for instance, HT, then this thing is equal to 0. Simply because HT is a first class Hamiltonian plus a set of first class constraints, all of which give 0 commutator. But moreover, now the Dirac brackets of any function of phase space with second class constraint is strongly, that is identically equal to 0. Indeed, some function phi with some chi, or chi s double prime, is written like this. But then in here, I have chi s prime with chi s double. But then this CSS prime was the inverse of chi s prime. So that by the definition in here, we have that this is delta S SW. The double, okay? So two terms cancel. So if it's identically equal to 0, it means that now we don't have a problem. It doesn't matter whether we use the constraints before or after quantization. So we can impose the second class constraints operatorily on states in order to quantize. We can put chi s on all the states is equal to 0. And then the Dirac brackets themselves are quantized, meaning they are replaced to the commutators instead of the Poisson brackets. So that was the review of Dirac quantization formalism. Now let's go over to BRST quantization. For BRST quantization, the Lagrangian was the Lagrangian. We've seen that the Lagrangian was the classical part plus the plus QB acting on, so QB, the BRST charge acting on the gauge fixing fermion. More precisely, since these are since QB is an operator, we usually write it as the commutator. The anti-commutator QB is anti-commuting. The anti-commutator of QB with psi. And BRST is like Dirac, since it's an extension of Dirac formalism, is itself based on the Hamiltonian formalism, which means in Minkowski's signature. And in Minkowski's signature, the gauge fixing fermion, in the way that we derived it before, as I mentioned, one can use in principle other kinds of gauge fixing fermions, but for regular gauge theories, this is enough. Is written as minus the ghost, BA, times the gauge fixing function, FA, plus alpha over 2 times Nakanishi-Lautrup auxiliary field, DA. Now, in the Hamiltonian formalism, we have initial and final states. We have time evolution, so we have initial and final states, I and F. And observables are obtained from the transition amplitudes from initial to final. Which means that this transition amplitude from initial to final should be independent of the Church of gauge, should be gauge invariance. In particular, in this kind of formalism, it should be independent on the gauge fixing function FA. So that means that a small variation of FA, such that, looking in here, the only thing that changes in psi is FA, so delta psi is BA delta FA. Then the variation, the path integral corresponding to the initial going to final states, path integral is its variation should be given by, so the variation of initial going to final is the path integral, and then when I vary the exponent, I get down the variation, so e to the I s times I delta s. And delta s itself, the only thing that changes is QB with psi, but again, Q doesn't change. Psi does change, and in psi, the only thing that changes is BA delta psi FA. So, well, yeah, I can forget what this delta psi is for the moment. But what I wanted to say is that then that I have I, bra F, anti-commuter QB with this delta psi times initial ket. And this variation must be equal to 0. As I said, the initial final transition probability amplitudes, sorry, should be equal to 0. So that means that this thing should be equal to 0. Now, if we assume, this is an assumption, which further, if you don't know the BRST variation, if you don't know the BRST charge, constraints QB, So if you assume that QB is Hermitian, that is QB dagger is equal to QB, then that means that, so expanding this anticommutator, there's one where QB is to the left. So I have, since I have QB dagger equal to QB, QB can be replaced with QB dagger. So F QB dagger is the dagger of QB kept F. And then the other term has QB to the right. So it's QB acting on ket E, I. So QB acting on ket F and ket I is equal to 0. But this was for whatever I and F. So that means that all physical states must be BRST invariant. So we have derived the condition that QB on a quantum state should be equal to 0. Quantum states, physical quantum states should be BRST invariants. For reasons that I'll explain shortly, we will call this QB, we will call this condition QB closed. On the other hand, the difference between equivalent physical states would be something that I will call QB exact, which means QB on something acting on something else. So psi prime ket being equal to a ket psi plus QB ket chi is equivalent to the ket psi. Why is that? Well, the condition for physical states, remember, is QB on physical state is equal to 0. So if I act with QB on this, I get QB on the first one. So if this is physical state, then this is equal to 0, plus QB squared on chi. But QB squared itself was equal to 0. That was derived as a condition on BRST, on the BRST charge. So this is equal to 0 itself, which means that psi prime is also physical. So if this is physical, this is also physical. That's one thing. But moreover, in order for these things to be equivalent, that means that the matrix element of the ket psi and of the ket psi prime with any other bra, or reversely, if I turn this to bras, matrix element with any other ket should be equal. So bra psi prime with any ket psi tilde is bra psi with ket psi tilde plus chi QB psi tilde. But remember, psi tilde must be physical. I mean, that was the point. That matrix element with some physical state should be unchanged. With some unphysical state, we don't care. So that means that QB on psi tilde should be equal to 0. That means that this matrix element is 0. And so indeed, psi prime with any psi tilde is equal to psi with any psi tilde. All right, so we have shown the equivalence of a physical state that differ by QB exact terms. But moreover, this equation must be preserved under time evolution. And in BRST quantization, we will define a Hamiltonian HBRST that gives the that generates the time evolution. So preserved under time evolution means that if I insert the Hamiltonian, so remember the time evolution is equal to is given by some a set of an infinite sum that contains various HBRSTs acting on the state. So so now I have the matrix element with psi prime with any psi tilde with HBRST inserted, and then psi prime, as before, is equal to the psi prime bra is equal to psi plus chi bra times QB. But I write this, so then I would have another term which would be chi QB HBRST psi tilde. But I choose to write that as chi HBRST QB psi tilde plus chi QB with commutator with HBRST times psi tilde. And now, since the matrix element has to be preserved in time evolution, that means that under time evolution, so this under insertion of HBRST, this should still be equal with the psi with the insertion, psi tilde with the insertion of HBRST. So this must be equal to this. Now, this thing is again equal to 0. Is equal to 0 because psi tilde is physical. So QB psi tilde is 0. So if this it must be equal to this, that means that this must be equal to this. But the states chi and psi tilde were arbitrary. So that means that operatorily, the commutator of QB with HBRST must be equal to 0. All right, so now let's understand what we've achieved. So in order to have this BRST quantization procedure, I have to define two objects, QB and HBRST. So this is based on the Dirac formalism. So there's a Hamiltonian in the presence of some constraints. But we have to define this HBRST and this QB in such a way that, remember, QB squared had to be equal to 0. That's a constraint we've defined from before and we've used throughout in here. And moreover, we've derived now that QB with HBRST must be equal to 0, the commutator. So we start with some classical Hamiltonian in the presence of some constraints, but then we have to construct some BRST Hamiltonian HBRST and some BRST charge QB, such that these two conditions are satisfied. Okay, so this is about operators. But then we have to construct physical states. And we've seen that physical states obey what? obey this condition, which is that physical states are QB closed, and physical states are equivalent under this condition. That is, physical states differ by equivalent physical states differ by QB exact terms. So from these two conditions, we say that physical states are states in the QB cohomology. So this condition to having this is QB closed. Sorry, closed here. So to have closed states modulo QB exact states. So QB homology is QB closed states modulo QB exact states. Or the Hilbert space of DRST quantization is the Hilbert space of closed states, of QB closed states, modulo the Hilbert space of QB exact states. Now, this is a notion of cohomology. Some mathematical language, simply because the cohomology of the exterior derivative D, defined as dx mu multiplied with del mu, is nothing but the physical, defines nothing but the physical states in electromagnetism. We have the, d squared equal to 0, since the anti-commuting product of dx mu del mu with dx mu del mu is equal to 0. And pure gauge fields in the absence of matter satisfy F, that is dA, is equal to 0. That is, they are declosed. And they are equivalent. So equivalent gauge field configurations differ by gauge transformations, which are the exact terms. Since the gauge transformation is A going to A plus d lambda. Okay? So from this, we derive that the cohomology of D over 1 forms is the cohomology of gauge fields, which means the physical states for the physical states of vanishing field strength. This is, you might say, this is something trivial. It's not something trivial if you give some non-trivial boundary conditions or some non-trivial space. So this cohomology is not non-trivial in general. Now, this cohomology of D is naturally extended to P forms instead of 1 forms in the Pth cohomology of D, and the notion of QB cohomology is completely similar to these cohomologies. All right.
I didn't understand that part. So can you go back a little bit?
Okay. So
Vanishing.
so I guess the point is that I didn't define forms, and maybe that confused you a little bit. So I defined. So this D is called the 1 form, since it only has 1 dx mu. So so it's dx mu times del mu times the normal partial derivative. But then D squared would be a 2 form. And as I said, a 2 form is defined as the so-called exterior product or anti-commuting product of the two D's. So dx mu del mu, anti-commuting product with another dx nu del nu. But these products are, I mean, it's the same D. So the anti-commuting product is 0. So since this is also commuting, right? So and then the field strength is the well, so it's a 2 form defined by dA, which means you still have dx mu, but now you have multiplied with d mu a nu, but dx mu is now antisymmetric. So you multiply with d mu a nu antisymmetric, it gives you the field strength, right? There's also some normalization of 1/2 to make things right, to have actually F equal to dA. Right, so dA is equal to 0, right? So A is your physical state, if you want, your Hilbert space, if you want. You're looking for the Hilbert space of A, and dA is equal to 0. But also the gauge transformation is A mu going to A mu plus D mu lambda, which in terms of 1 forms is A going to A plus D lambda. But then that means what I said before. So the A is equivalent with A plus D lambda, which is what we called the exact. So the Hilbert space of things of vanishing field strength, of gauge fields of vanishing field strength, is D closed the closed fields modulo the exact fields. Okay, so that is the cohomology of the operator D, this operator, where the Hilbert space is 1 forms. So the cohomology of D over 1 forms. And this is, in physical terms, this is cohomology of gauge fields, that is physical states for fields of vanishing field strength.
Why only vanishing field strength?
Yeah, now, as I said, this sounds kind of trivial, because you might say, well, then I can gauge transform things to 0. But it's not if either the space is non-trivial, the space it's maybe like a sphere or a torus or something, or there's some non-trivial boundary conditions, right? In this case, the cohomology is non-trivial. If you're looking for you know, flat space with no boundary conditions, then the cohomology is trivial. You know, you can always put a gauge field to 0 by gauge transformation if the field strength is 0. But in general, it's not. Okay, so this cohomology of D over 1 forms in general is non-trivial. Now, this notion can be extended, the operator D can be extended to act not only on these A's, which are one forms, but to act on P forms, meaning product of P, anti-commuting product of P of these things. That's called the Pisco cohomology of D. So these cohomologies are the most common in mathematics. And as I wanted for you to notice that the first cohomology, the cohomology of one forms, is something very simple. It's just fields equivalent, physical states for gauge fields of vanishing field strength. Okay, but now when we're doing BRST quantization, what we talked about here was classical, right? This was about classical functions. But now we're talking about BRST quantization, and in BRST quantization, I have this operator QB instead of the operator D, and I have the physical Hilbert space of BRST quantization is the cohomology. That is the Hilbert space of closed states modulo. That means eliminating equivalences of the states which are QB exact. Okay. All right. Okay.
So the field strength needs to vanish at infinity. That's what you mean, vanishing field strength.
No, vanishing field strength everywhere.
Everywhere.
Everywhere. That's why I said this sounds trivial. If the field vanishes, field strength, if electric magnetic field vanishes everywhere, this to you sounds trivial because you think of R space, which doesn't have boundary conditions, and it's not a sphere, right? Or it's not, or a torus or something. But if you think of, so there are applications where you have to think of the electromagnetism on a sphere, on a torus, or electromagnetism where there's a boundary condition. There's a certain boundary condition, not at infinity. In this case, even if E and B is equal to 0, there's still some non-trivial field, non-trivial states. Okay, that's the cohomology. Okay, maybe, yeah. Maybe people didn't think about that when talking about electromagnetism, but it's something that is important. All right, so this was BRST quantization defined. Now let's apply it. The example, the sort of trivial example. So we're kind of at some midpoints. So we haven't defined yet the general formalism. So because we talked about QB and HBRST, but I didn't tell you what that is. I mean, or how do you start constructing it? But to understand what we've done until now, let's do a trivial example, which is electromagnetism in Lorenz gauge. So these are abelian gauge fields, which means the structure constants F, A, B, C are 0. And the BRC transformations then are what? So variation of A normally is covariant derivative on C lambda, but if A, B, C is 0, so it's just normal derivative of C. BRC variation of B is 1 over alpha times the gauge fixing function, which is d mu a mu. And the variation of C is proportional with FABC, so it's just 0 now. This is very trivial, BRST transformation. And consider the canonical transformation, canonical quantization for A mu BC without taking into account gauge invariance and constraints. So, you know, C and B would be, they're complex fields. They would, in principle, be expanded in like usual complex scalars. C e to the IPX, C dagger e to minus IPX, and same for B. And A mu, I just put some index mu for the moment, since I didn't talk about gauge invariance and constraints. Now, the BRC transformation acts by anti-commuting with B, with QB. I mean, sorry, commuting or anti-commuting, depending on what you act on. If you act on a boson, you commute. If you act on a fermion, you anti-commute. So the variation of A mu is I times commutator lambda. But this should give d mu c lambda, from which I learned that QB with A mu is plus P mu C, and QB with A mu dagger is minus P mu C dagger, just comparing the variation. So I have these expansion, and I compare this, I substitute in here, and compare the two sides, and find this. I do the same for B, since the variation of B is I. Now, B is anti-commuting, so it's anti-commuter with QB times lambda. But the variation of B, we saw that it's supposed to be 1 over alpha times d mu a mu. And again, I substitute B and A mu, these things, in these two relations, and putting them equal to each other, I find that the anti-commuter of QB with B is 1 over alpha. Since it's in momentum space, del mu is replaced now with P mu, or P mu A mu. And the dagger 1 has a minus. Variation of C, again, C is anti-commuting, so it's anti-commuter. Then reality properties, B is real, but C is imaginary, so the different I's in here. The variation of C is equal to 0, which means that, in fact, I get that QB with C is equal to 0, and QB with C dagger is also equal to 0. Okay. Now, let's so we've we've constructed the so this was a classical expansion, and we've constructed the classical commuters or anti-commuters of QB with these coefficients. And now let's construct the quantization. In particular, let's construct the Hilbert space of physical space. So these commuter anti-commuters, so at the classical level, there would be Poisson brackets, but at the quantum level, they turn into commutator and anti-commutator. So I said that the Hilbert space of physical space is the cohomology of QB. That is the Hilbert space, the Hilbert space of QB closed states modulo QB exact states. So let's so QB closed states, QB psi equal to 0. And let me construct a state. So I have this A mu and A mu dagger. And A mu dagger turns into creation operator, right? So let's consider a state where I act on some other physical state psi tilde, which means psi QB on psi tilde is equal to 0. But now A mu dagger will create something. For the moment, I haven't defined exactly what. And I have to multiply with some polarization E mu. So if I want to impose that QB on psi is equal to 0, then I write this as AB dagger, so time with QB on the right, then plus the commutator, right? So the commutator or minus the commutator. So the commutator, as we saw, was plus commutator. No, commutator, as we saw, was equal to this. Commutator QB with A mu dagger was equal to this. So I substituted in here minus P mu C dagger P. Then I still have polarization E mu to the left and the original physical state psi tilde to the right. But this was physical state, so QB on psi tilde is equal to 0. So QB on psi then is equal to this. Therefore, we find that in order to add something with A mu dagger to a physical state, then that QB psi is equal to 0, we have to have E mu P mu is equal to 0. All right, which means that the additional physical state has to be transverse. So now you can start with the vacuum. That's also a physical state, and you say that you have to always add transverse photons for which the polarization multiplied with P mu is equal to 0. now, on the other hand, let me consider adding B dagger to psi tilde. Psi tilde was physical state. If I add B dagger, then I want to check if this is physical. So QB, B dagger, psi tilde, again, is minus B dagger QB, psi tilde, plus the anticommutator, which is equal to this. So I substituted in here. But then QB psi tilde is equal to 0, because psi tilde is physical state. So QB on this B dagger on a physical state is equal to this. Okay. All right. Now, what happened? So I said that the Hilbert set of physical states is the cohomology. So closed states modulo modulo exact states. So so, but we know we kind of know what happens. So if I add to the making a gauge transformation basically means adding to the polarization E mu a P mu times some number. So E mu, so psi of E mu plus B P mu is psi of E mu, the original state. The original state, this one, plus the state where I add beta P mu. So instead of E mu, I add now beta P mu with A mu dagger P and psi tilde. But then, I see that this thing, P mu A mu dagger P psi tilde, was equal to this. So this thing then is equal to minus alpha QB B dagger psi tilde. Okay. So that's as we said. So for as we said, the state psi of E mu is equivalent to the state psi with E mu plus beta P mu, because I add a term which is QB exact, namely QB of something else. But so QB. So this is some state chi. So it's QB on chi. On the other hand, we also learned that we also have learned that QB on this B dagger psi tilde is non-zero. This thing is non-zero. So adding B dagger to a physical state does not generate another physical state. Okay, so that means there are no states with ghosts B in it. And we can also find the same thing we repeat the same thing we did here for B. We repeat it for C, and we find that C dagger so remember that the anticommutator of QB with C dagger is equal to 0. So we write this. We write QB C dagger psi tilde is minus C dagger QB psi tilde, but this is equal to 0. And then basically we find that this C dagger psi oh, well, yeah. So sorry. So I find something trivial in this way, but a better way is to look at this equation and obtain that C dagger P on psi tilde is QB on this psi divided by E mu P mu. So C dagger psi is QB on something that is equivalent to 0. In the cohomology is equivalent to 0. This is QB exact, that is, it's equivalent to 0. So so that means that you cannot have B's and C's in physical states. You can only have things like this, E mu, A mu dagger, and you can add to E mu, you can add beta P mu. All right. So the Hilbert space is composed only of transverse photons, as we saw. So the photons were transverse because we saw that the E mu was to be constrained by E mu P mu equal to 0. All right. So we found that indeed the QB cohomology for BRC quantization of electromagnetism indeed generates the right physical space, only of transverse photons. All right. Okay. So this was an application that was kind of trivial, but now let's continue with our BRC quantization to a more general level. So as I said, we need to define QB and the BRC Hamiltonian. And they have to satisfy that QB commutes with the HBRST and QB squared is 0. And then construct the Hilbert space as a QB cohomology. Well, so before we do anything, let's show that QB squared is actually needed. It's not, I mean, we've used it several times, but we kind of assumed it, but let's show that we actually need it. So so we want that the gauge choice does not change the commutation relation, that QB HBRST is 0. So any variation of the Hamiltonian induced by the gauge choice should preserve it. So it means QB with delta HBRST should also be equal to 0. But we saw that delta HBRST is minus QB with BA. The variation of the gauge fixing fermion was BA times delta FA, the variation of the gauge fixing function. So we have then that 0 is the commutator of QB with delta H bar ST, which is anti-commutator of QB with BA delta FA. That is to say, is the commutator of QB squared with BA delta FA. And since delta FA is arbitrary, and also BA is arbitrary, that means QB squared must be equal to 0. There is I mean, it might have been clear to you, but there are actually subtleties compared to the relating to the path integral. But there is an actual theorem by Fradkin and Wilkowicki that the partition function, so path integral e to the exponent of I times the quantum action, is actually independent on the gauge fixing fermion. So we need to construct QB and H bar ST. And the way this is done is order by order in the number of fields. So we start in quadratic terms, then cubic, then quartic, and so on. But then you have to define somewhere, you have to define the first order for QB and H bar ST. So so H bar ST is Hamiltonian formalism, but let's think about Lagrangian formalism. So let's write the quantum action as the integral of, so here you have to write some variables qi dot times momenta pi, and also equivalent minus H bar ST, but also so H bar ST is a remember we have noted before that we had we had the classical part, and then the anticommutator of QB with the gauge fixing fermion. So so this is sort of starts off like the classical part, and then I have to add QB with the gauge fixing fermion. But moreover, talking about the action, I would think, classically I would think that it's Q dot P minus H. But now in the quantum action, I would have also Lagrange multipliers lambda mu. Lagrange multipliers for constraints. Remember, I have some constraints. And then also the constraints themselves. So so the conjugate momenta to the Lagrange multipliers are actually the first class constraints. Remember, the second class constraints will be related to the Dirac bracket. So only the first class constraints remain. So the first class constraints are related, conjugated to the Lagrange multipliers. So okay, so well, sorry. So there's a number of them are conjugated to the Lagrange multipliers, but there's still others that are called phi alpha, and together the first class constraints will be called GA. And then these being first class means they obey an algebra, right? Remember, it means that they're weakly, the commutator with another first class constraint is weakly 0, it means is FABC. So GAGB is FABC GC, obey an algebra. We also define the ghost phase space as, so we have some C's and some B's, right? Some ghosts and anti-ghosts. Now C, together with minus the conjugate momentum of B, is called eta A, and PA is minus B together with the conjugate momentum of C. Conjugate momentum means I find the Poisson brackets of C with P with C is delta, and beta of P with B is delta. And then that means together with this, I found that eta A with PB is also delta. Right. So the minus is sorry, the minus is just because this is a those are anti-commutative, B's and C's are anti-commutative objects. All right, so we've defined these objects, GA and eta A. And so eta A was defined this way, and PA this way. So we define this object, define this object. So so now let's talk about HBRST and QB. So HBRST will start from we'll start from the classical term. That's why we had the that's why we put here Q dot P minus HBRST, but we separated the quantum part psi with QB, and then we had, so, which was in the Hamiltonian, and then we had this this extra something dot conjugate terms, and QB will start off like this. So we'll start off with eta A GA, that's the quadratic part, and then, you know, in principle, so this part and this part it's quadratic, so you have to start somewhere. So you can show that you can add this term eta 1/2 eta c eta b pa fbca with minus the c in here. Minus to the c refers to being commuting or anti-commuting. And then we can still satisfy QB squared to this order. You can still satisfy QB squared equal to 0 to this order using the Jacobi identities, which refers to a quadratic combination of f's. And then, as I said, the quadratic, the BRST Hamiltonian starts at the classical term, but then you have to add one extra term. And this extra term will be of the type eta A PB with some coefficients VAB. And these coefficients are found from commuting the classical Hamiltonian H0 with these GAs. These GAs that include the first class, all the first class constraints, the ones that are explicit and the ones that appear as conjugate momenta. Now you have to, so the conditions we have to impose is not just QB squared equal to 0, but also QB commuted with HBRST is equal to 0. And since this part in here is quadratic, and this part is cubic, so this will generate the need to introduce an extra term in here, and then a need to extra term in here, a term in here, term in here, and so on. So this will be, so imposing the two conditions, QB squared equal to 0 and QB with HBRST equal to 0, will generate an infinite series in principle in both QB and HBRST in increasing number of fields. But in practice, for interesting things, this series terminates at some point. Now in QB, you can show that you can have, in fact, you have a number n of etas and the number n of corresponding p's with some coefficients u, n. At the sorry, this is QB at the nth order. All right, so yeah, so you can, from the definition U0 is GA and U1 is this combination, the structure constants times these numbers. All right, so I've showed to you how to calculate HBRST and QB. And, you know, I said terms quantum in here with respect to the action, but the formulas that I actually wrote could have been thought of as completely classical, could have been thought of as just Poisson brackets in here, all of these Poisson brackets. In fact, I even said Poisson brackets. Yeah. So for all these algebras to be Poisson brackets. So quantization itself means replacing, sorry, I said, well, this one is Poisson, but in general, you yeah, this has no extra components. It's really Poisson, but in general, the commutators are Dirac commutator and Dirac bracket, and to quantize, you replace the Dirac bracket with a commutator or anti-commutator, and you have to find the physical Hilbert space as the space of states in the QB cohomology, like we saw for electromagnetism. All right. Let me just see how much thing I have to say. Yeah, so now we go to the example that we would be most interested in. Well, actually, most interested would be something like QCD or the standard model, but let's consider as an example just pure Young-Mills. So I will do the part until here, not the actual quantization, which means simply replacing the Dirac brackets with the commutator and finding the QB cohomology. That's more complicated, but just to show this formalism, this general formalism, how it's applied in the case of pure Young-Mills. So pure Young-Mills means an action, classical action, which is -1/4 in Minkowski space. It's -1/4 FA mu nu squared. Now I want to go over to Hamiltonian formalism, so I have to separate space and time, and I write this as -1/4 Fij squared. This meaning that I will have the magnetic field, magnetic Young-Mills field, BA, and then this part in here will generate the electric-like part. So this is magnetic part plus electric field. So electric field is F0IA, and then this amounts to A dot IA minus DI A0A, covariant DI. Because I have here A dot I, that means that the momentum conjugate to AI is the electric field. This, if I take the derivative with respect to this, I find the electric field. Okay. And like in the case of electromagnetism, I find no momentum conjugate to A0. There's no A0 dot in the action. So that means I have a primary constraint for pure Mills that is P0A is equal to 0. So to find the Hamiltonian, I write A dot IA times the momentum minus the Hamiltonian Hamiltonian I'll choose to write as I'm sorry. I think yeah, so yeah, I kind of got ahead of myself, but my point is if I write A dot A electric field minus the classical minus H0, I find that H0 is the classical Hamiltonian, which is E squared over 2 plus B squared over 2, the usual thing. But then I can also define the naive Hamiltonian IHL by adding by partially integrating. So there's a term where I partially integrate di, this di acting on A0. So if I get a term from here, A dot I A times E, which is this, and then I get a term minus di A0A times the same electric field. But then in this term, I partially integrate di, and I get A0 di electric field di. And then I define the naive Hamiltonian HL as H0 minus this combination, A0 di EI. But I find that the time evolution of the primary constraint P0, that is P0 with HL, is equal to minus di EI 0. So that's my secondary constraint. So the secondary constraint, the extension of the Gauss constraint of electromagnetism, is covariant derivative of the electric field is 0. And we can check there are no other secondary constraints, since the Poisson bracket of this constraint with HL is 0. And we see that A0A appears as a Lagrange multiplier for the secondary constraint. Now let's find the algebra of constraints. Well, for P0 with P0 is 0. That's easy to check. P0 with di with the secondary constraint. This is normal derivative on remember ER electric field is pi, so it's normal derivative on pi plus this term with FABC, but this bracket is still 0 since I don't have A0 in here. But then the secondary constraint with itself is not 0. If we look at this, we find that we have an AI with pi that will give a non-zero bracket. And when I do the calculation, I find that I find something proportional again to the secondary constraint. And moreover, what that is what is expected is the coupling times FABC. Since I have indices A, B on the left and C on the right. All right, so the algebra of all of the constraints is 0, 0, GFABC. Now, these are all of the constraints, both the primary and secondary constraints, obey an algebra. That means they are first class. So that means that the Dirac brackets are just the Poisson brackets. There's no secondary constraint, second class constraint. That means Dirac brackets are just Poisson brackets. That means that the constraints and phase space coordinates, the GAs, are written like this. So this is a constraint times so yeah, these are all the first class constraints, GA. And then eta A is CA minus PBA, and PA is PCA minus BA. So these are all the objects that we needed to construct QB and HBRST. And with HBRST, you start with H0, which is the electric field plus squared over 2 plus B squared over 2. But so one thing I had to point it out in here, since in the Hamiltonian formalism, I have to replace inside the Hamiltonian, I have to replace the electric field with momentum PIA. So EIA is equal to PIA, so I have to replace this in here. So HBRST starts off like this, and then QB starts off like so GA eta A, right? Sorry, eta A GA, and then the second term would be eta P. So eta G, so that's C times DIA, and then minus PB times P0, right? And then the second term is the second term, the term cubic in field is eta P, right? So let's say C times PC with coefficient FCBA with minus 1/2, right? And then I could write P. Yeah, I could write other combinations, but yeah, why there are 0? I don't see right now why the other combinations are 0, but anyway, at least I'm sure that I have this first order term. The naive Hamiltonian, as I said, was equal to this, A0 times the A0 minus A0A times yeah, it's covariant derivative on the momentum, but why remains just del I? I think it's di. I think it's a typo here. Yeah, I think this should be the covariant derivative on PIA. All the constraints are first class, so there's no need to extend it. So E8 extend the Hamiltonian equal to the naive one. And the constraint P0A does not appear with its Lagrangian multiplier since it can be absorbed in this term. Now, in the Dirac formalism, the classical action was written like this, with some Lagrange multiplier. But now in the BRC formalism, the quantum action is written like this. So I have the Q's, which are AI, A, and the P's. But then I have the Lagrange multiplier A0A. So this is Lagrange multiplier lambda dot times P. And then I have still this eta A PA terms. And then minus Lagrange, the H0 term, and plus the gauge fixing part. Yeah, so as I said, the next step would have been to find a QB cohomology to find physical states. That is a little bit more involved, so I'll not do it. But basically, one finds. One finds only transverse gluons, in some sense. Yeah, Dirac brackets are equal to Poisson brackets are replaced with commutators. That's kind of obvious. And finally, just a couple of words about the yet another extension. As I said, there's the further extension is the Batalin-Vilkovitsky formalism or field antifield formalism. Field antifield refers to the fact that we introduced in order derive the Lee-Zahn-Stein identity, we introduced as a trick sources K and L for the nonlinear terms QBA and QBC. And these things are called antifields for A and C. So it's antifield times QB times field. In the BV formalism, one introduced antifields also for the other ones, for B and D. We didn't find a need in order to derive these understand, and then we didn't find a need for this since QB of B and QB of D was not nonlinear, was linear in field. But in field antifield formalism, we do introduce. And another point about the BV formalism is that it's a Lagrangian one, whereas the BRST one is a Hamiltonian formalism, and also a Lorenz covariant one. So that's why a need to introduce something else, since we already found almost everything that we wanted to find. And the formalism is somewhat more simple and more elegant from the fact that the BRST charge equals the antifield extended quantum action S. So S and QBRST are this extended quantum antifield extended quantum action S is also equal to QBRST. So that means the variation, BRST variation of the fields is a bracket of F of the field with S times lambda. And instead of having two equations, two constraints, that we needed to solve, QB squared equal to 0 and QB commuted with HBRST is 0. In the BV formalism, there's a single one that unites this, and this is the master equation, which is the bracket of S with S equal to 0. So this replaces QB squared equal to 0 can be thought of as anti-commutator of QB with QB, but QB is S, so this is part of it, and then this also includes this other bracket. All right, so this is everything I wanted to tell you today, and after doing all of these formal things and talking about Yang-Mills and pure Yang-Mills and very little about pure Yang-Mills with matter, finally, starting from next lecture, we'll talk about some physical stuff, namely QCD. So we'll define what QCD is, and we'll find some applications. All right, so this is it. Do you have any questions? Well, can somebody check that you can still hear me?
Yes.
Okay, thank you very much. So that means I will end the lecture here, and we'll talk on Thursday. Oh, one more thing that I forgot to say. Next Tuesday, it would be good to do this now. So next Tuesday, I have a meeting of the CCPG with Teoria, So in the morning. So would it be possible for you to move this in the afternoon next Tuesday? Does anybody have another class online or something?
Yeah, for me, it's okay.
Well, I don't hear anybody else complaining, but just to be sure, I'll send you an email to confirm. But anyway, just to inform you. So I'll see you on Thursday morning, 9 a.m. Okay, bye.